In this topic, we will study how does an electric dipole behave when it is placed in an external electric field, uniform as well as non-uniform. So we have already seen what is a dipole. Dipole means an arrangement of positive and negative charges separated by a very small distance. So we have a plus charge and we have a minus charge, and they are separated by a very small distance. And I gave you some examples like all polar molecules actually. Even water molecule, that is an example of electric dipole. HCl, NaCl, all those molecules are examples of electric dipole. When we keep an atom in the electric field, it also behaves like an electric dipole because the positive charges, protons, they experience force in the direction of the field, negative, that is electrons, opposite to it. So the centers of plus and minus charges, they get displaced, they are separated, so it starts behaving like an electric dipole. Then there is a quantity, product of charge on any one, plus or minus, and the length of the dipole, the distance between the two charges, that is called the length. This is dipole moment, and this is a vector quantity. Its direction is taken as negative to positive charge, dipole moment. Now we will study what will happen if I keep an electric dipole in an electric field, external electric field. So let's first consider uniform electric field. And uniform electric field means constant in magnitude and in direction. Same direction, same magnitude. It is represented by parallel and equidistant lines. And let E be the intensity of the electric field. And let me keep an electric dipole in this, and plus and minus charges separated by a distance L. And let us take this as theta. So dipole moment is in this direction. This is the direction of dipole moment, and this is the direction of electric field, and the angle I have taken theta between them. Okay. So it is placed at an angle of theta. Theta is the angle between electric dipole moment and electric field. What will happen now? Plus charge always experiences force in the direction of electric field, and minus charge opposite to it. So plus charge will experience force in the direction of the electric field. Negative charge opposite to it. And the value of this is same. QE because electric field is same. Intensity of the field at this point, intensity of field at this point is same, so force will be same. But one will be along electric field, another opposite to it. So what is the resultant force? If we net force is 0 on this dipole, because plus and minus they experience equal force but in opposite direction. Okay, net force is 0, but net effect of these forces is not 0. How? If I take this pen and on this end there is a force in this direction, and on this there is a force in this direction. I just use two strings. One is pulled in this direction, one is pulled. What will happen to it? It actually comes like this. See, two forces will exactly cancel out. They will not produce even this effect if they are not along the same line. But whenever two forces are equal in magnitude but not along the same line, so they will cause rotation of the body. They constitute a torque actually. Right? So this dipole will rotate and will try to align along the electric field. And how much is this torque? How do we calculate torque? Torque is calculated, we can either take a central point and then calculate the torque for this, or we can just take force into the perpendicular distance between the lines of action. One force is acting along this line, another force is acting along this line, so we may take this distance. Center maybe we can do from here also. So this torque clockwise, this is also clockwise, both of them are producing the effect in the same direction, so it will be added. Or one way is this QE, one force, and the perpendicular distance between these two lines. This is how we calculate force. So this is one line, this is another along with the forces. What is the perpendicular distance between them? This is L, this is theta, so this is actually L sine theta. So QE, L sine theta, QL, E sine theta, QL is PE sine theta. Now let us see what is the direction of this torque. This dipole is rotating clockwise actually. It is trying to come along the field. So what will be the direction of the torque? Torque is actually, see, how do we find the cross product of two vectors? Suppose I ask you find out P cross B and E cross B. P cross P is, we have to use right hand screw rule, turn our fingers from first vector to second through the smaller angle. So P and E have two angles between them, one this and one this. So this is, I am going through a bigger angle. This is through the smaller angle. The rule says that turn your fingers from first vector to second through the smaller angle. So this tells us actually the sense in which the rotation is actually taking place. So P cross E is this, E cross P is this, right? So this is coming like this, so it means the direction of torque is into the plane of the paper and perpendicular to P and E, this plane. So it is actually P cross E. This is how we find out the direction of cross product, any cross product. If there is any confusion, we can take few more examples. A and B. What is the direction of A cross B? Turn your fingers from first vector to second through the smaller angle. This. B cross A. This. So inward. Cross product is always perpendicular to both the given vectors. So it is into or out. In this case also, P cross A is in, and the direction in which our fingers turn actually tell us the direction in which the rotation takes place. Okay, so P cross E is the value of torque, or PE sine theta. If theta is 0, torque will be 0. Theta 0 means if the dipole is, it is like this, because P and E, they are in the same direction, theta 0, so torque is 0. If theta is 180, again torque is 0, but this time P is this, minus 2 plus, and E is this. But even in this case, the torque is 0. What is the difference in these two situations? Let's discuss these two situations. Uniform field once the dipole is like this, and in another case I am keeping it like this. So in this case P is this E is this, torque is 0. Here also torque is 0, here theta is 0. P is this, E is this, theta is 180, but torque is still 0. But even then, we can think about it that there is some difference. These situations are not identical, even if the torque is 0. Torque 0 means we say that the dipole is in equilibrium. See, dipole in an electric field, uniform electric field, force is 0, so it is translational equilibrium. In this case, it is rotational equilibrium also. So when force is 0, translational equilibrium. We have seen that whenever a dipole is kept in uniform field, uniform electric field, net force is 0, so there is translational equilibrium. Torque is 0 only when this is along the field, whether parallel or anti-parallel. Otherwise there is torque. So there won't be rotational equilibrium then. But in this particular situation, there is rotational equilibrium too. But what type of equilibrium this is and what type of equilibrium this, or are they same? Just imagine. How do we conclude about the equilibrium? I'm giving you one example. Suppose I keep this like this, and so this is in equilibrium, net force onto it is 0. Now I displace it and leave it. It comes back. It will return to its position. Now if I somehow balances this like this and I displace it, will it come back? No. Though if I balance it somehow, it means the force acting onto it is 0, the torque acting onto it is 0, but when I am displacing, it is not coming back, while in this case, it is returning. This is what happens here too. If I slightly displace it, let me take it here. What will happen now? I am slightly displacing it and then leave it. This experience force in this direction, this experience, so it will again come to its initial position. What will happen here? Now again let me this, I take positive here and negative here. Slightly displace it. Positive charge experience force in that direction and negative. So it will, instead of coming back to its position, it will actually turn over. This type of equilibrium, we call it unstable equilibrium. And this is, we call stable equilibrium. So theta is equal to 0 is a position of stable equilibrium. Theta is 180, it is unstable equilibrium. From a position of stable equilibrium, if we displace the dipole, it returns to its initial position, but here it will turn over. Unstable equilibrium. Okay, we have done so far electric field which is uniform. What if the field is not uniform? Say I take the example of a positive charge. Point positive charge, the field is not uniform. It decreases as we move away. So, and I keep a dipole here. What will happen in this case? This will experience a force in the direction of the field, which is QE. This will experience a force opposite to the field, which is QE dash. In uniform field, so what will happen now? This is bigger than this. As we move away from point charge, the field decreases. So this is more. So it means this dipole will start moving towards it. In the same expression that we derive, we have taken the force on plus charge and minus charge. Equal and opposite. QE and it was also QE. So they cancel out, net force becomes 0. If the field is not same at these two locations, this is more, then this will move like this. If this is more, this will move like this. So the dipole will not even be in translational equilibrium. So we can generalize the result. In uniform electric field, net force is 0, torque may be or may not be. But in non-uniform field, there will not be translational equilibrium. So there may be translation motion, rotational motion in non-uniform field, and uniform field, no translation motion, only rotational motion.